Dear students, welcome back to the lecture series on solid state. In this session, we will have a detailed discussion on the effect of interaction between constituents on the melting point and boiling point in various crystalline solids. And then we will have a discussion on crystallization process. We will be discussing different stages of crystallization that includes nucleation and growth of crystals. Finally, we will see some examples of crystallization process. So, before moving on to today's session, let us discuss the answers of assignment questions of the previous class. So, the first question was, the molecules in polar molecular solid are held together by, we have four options. Option A, dipole-dipole interaction. Option B, London forces. Option C, ionic bond, and option D, metallic bond. We know that a polar molecular solid are held together by dipole-dipole interactions. The correct answer is A. A polar molecule means it can act as a dipole. So, such molecules are held together by dipole-dipole interactions. Question number 2. Which type of solids are formed by three-dimensional arrangement of cations and anions bound by strong electrostatic force? You have option A, polar molecular solids, option B, ionic solids, option C, covalent solids, and option D, metallic solids. In the question, you can see a three-dimensional arrangement of cations and anions. So, cations and anions means they will be attracted together by electrostatic force of attraction, which is also known as ionic force. So, ionic force can be seen in ionic solids. So, the correct answer is option B, ionic solids. Question number 3. Which type of crystalline solid is also called as giant molecules? Option A, ionic solids, option B, covalent solids, option C, polar molecular solids, and option D, metallic solids. We have seen that covalent solids or covalent network solids held together by strong covalent bonds can result in a continuous network producing huge crystals, and that is why they are called giant molecules. So, the correct answer is option B, covalent solids, which are also known as giant molecules. Question number 4. Which of the following are responsible for high electrical and thermal conductivity of a metal? Option A, ions, option B, covalent bonds, option C, free H plus ions, and option D, free and mobile electrons. High electrical and thermal conductivity of a metal is due to the presence of metallic bonding, and in metallic bonding we have seen that positively charged metal ions are surrounded by a pool of delocalized electrons which are free to move. So, these free electrons are responsible for high electrical and thermal conductivity in metallic solids. So, the correct option is option D, free and mobile electrons. Now, the last question was, which of the following is non-conductor of electricity at solid state but can conduct electricity in the molten state or when dissolved in water? Options are option A, non-polar molecular solids, option B, metallic solids, option C, ionic solids, and option D, hydrogen bonded molecular solids. Non-polar solids and hydrogen bonded solids are generally poor conductors of electricity. And metallic solids, they have high thermal and electrical conductivity. So, what about ionic solids? Now, ionic solids are generally poor conductors of electricity in the solid state, but in the molten state or when dissolved in water, the ions are sufficiently free to move and can conduct electricity. So, the correct answer is option C, ionic solids. So, these are the answers for the questions that we discussed in the previous class. So, now we will move on to today's session. In the previous class, we have seen different types of crystalline solids. They can be molecular solids, covalent or network solids, ionic solids or metallic solids. And these solids are characterized by different types of intermolecular forces such as ionic force or electrostatic force of attraction, covalent forces, weak dispersion forces or London forces, dipole-dipole interactions, hydrogen bonding, metallic bonding, etc. Now, let us see how these intermolecular forces affect the melting point and boiling point. Consider a solid. We know that in solids, the constituent particles are tightly packed, they are fixed at their perfect positions and the freedom of movement is restricted. Now, what happens when we apply heat? The addition of heat causes the structural units of a crystal to wiggle in their places. As you can see here, they just start vibrating more or wiggle in their places. Now, what happens if we continue applying heat? Eventually, these structural units, that is they can be atoms, ions or molecules, these structural units break out of their lattice sites and begin to slide past one another. Now, this is the moment at which the solid begins to transform into liquid, and this is nothing but melting. So, melting is the stage at which the solid begins to transform into liquid. Now, the temperature of the system will remain constant until the whole of the solid will melt into the liquid phase, and this constant temperature is called the melting point. So, the constituent particles in a solid will begin to break out of their lattice sites and they begin to slide past one another on applying heat, and this is the point at which the solid begins to transform into liquid, which is called melting, and the temperature of the system will remain constant until the whole of the solid melt into the liquid phase, and this constant temperature is called the melting point. Now, what happens if we add more heat energy to the system? So, addition of more energy results in complete overcome of the intermolecular forces, or that is the moment when the liquid begins to transform into gas, and this is called boiling. As you can see in the figure, the constituent particles attain more energy, they have more freedom of movement, so they will just start transforming into the gaseous state, and the stage at which a liquid begins to convert into the gaseous form is called boiling. The temperature of the system will remain constant until the whole of the liquid melt into its vapor phase, and this constant temperature is called the boiling point. So, we have seen about melting point and boiling point. Now, let us see how the presence of intermolecular forces in various crystalline solids affect these melting and boiling points. First, let us discuss the case of non-polar molecular solids. We have seen that in non-polar molecular solids, the constituent particles are either atoms or non-polar molecules. They are held together by weak dispersion forces or London forces. They are very soft solids with low melting points. For example, if we take the case of solid carbon dioxide, which is commonly known as dry ice, the solid, liquid and gas phase of CO2 can exist in equilibrium only at a temperature of minus 56.6 degrees Celsius and a pressure of 5.1 atmosphere. The liquid carbon dioxide cannot exist at pressures lower than 5.1 atmosphere. Now, what happens when the pressure is lower than 5.1 atmosphere? We can see that at 1 atmosphere pressure, solid carbon dioxide directly sublimes into the gas phase at a temperature of minus 78.5 degree Celsius. So, we can see that carbon dioxide, which is a non-polar molecular solid, has an extremely low melting point of minus 78.5 degree Celsius due to the presence of very weak dispersion forces. Another example for a non-polar solid is solid nitrogen. So, in solid N2 or solid nitrogen, at standard atmospheric pressure, the melting point is very low. It is about minus 210 degrees Celsius and its boiling point is minus 195.8 degree Celsius. So, when we consider non-polar molecular solids which are held together by very weak dispersion forces, they have very low melting points and boiling points. Next is polar molecular solids. We have seen that the constituent particles are polar molecules held together by strong dipole-dipole interactions, and it is made of molecules which have a permanent dipole moment. Polar molecular solids generally have higher melting points when compared with non-polar solids. For example, hydrogen chloride, which is a polar molecule, has a melting point of minus 114 degree Celsius and a boiling point of minus 85 degree Celsius. Similarly, sulfur dioxide in the solid state, they have a melting point of minus 72 degree Celsius and a boiling point of minus 10 degree Celsius. So, this is comparatively higher when compared with non-polar molecular solids. So, next is about hydrogen bonded molecular solids. We know that in hydrogen bonded molecular solids, the constituent particles are molecules and they are held together by hydrogen bonding. In hydrogen bonded molecular solids, the melting and boiling points are higher than those of the normal polar solids that do not have hydrogen bonding. These are examples for hydrogen bonded molecular solids. We have hydrogen fluoride, ammonia, etc. This table shows the trends in the melting point and boiling point of group 16 hydrides. On the top, you can see water, that is H2O, which has very strong hydrogen bonding compared to the other three in the series, that is H2S, H2SC, hydrogen selenide and hydrogen telluride. So, among these four, H2O has the strongest hydrogen bonding because of the highly electronegative oxygen atom. Okay. Now, let us see about the variation in the melting and the boiling point. The general trend is that there will be an increase in the melting and boiling point down the group because of the increase in the molecular mass. But when we look at this, we can see that with the exception of water, the other three in the series follow that trend. That is, there will be an increase in the melting and boiling point down the group. But water is an exception. Here you can see that the melting point of ice is 0 degrees Celsius. The boiling point of water is 100 degrees Celsius. Now, why this high melting and boiling point compared to the other three in the series? And this is due to the presence of hydrogen bonding. We have seen that ice has a relatively high melting point of 0 degrees Celsius compared to the other group 16 hydrides. So, water molecules are attracted to each other due to hydrogen bonds, and we know that hydrogen bonding is a special case of dipole-dipole interaction. It is stronger than normal dipole-dipole interactions. So, when ice melts, these strong hydrogen bonds must be broken, and this requires more energy. So, that is why the melting point of ice is relatively higher compared to other group 16 hydrides. Another example we can see ammonia. Ammonia has a relatively high melting and boiling point when compared to pH3 or ASH3. When compared to the other two in the series, ammonia has a high melting point of minus 77.7 degrees Celsius and a boiling point of minus 33.35 degrees Celsius. Again, this is a direct consequence of strong NH hydrogen bonding seen in ammonia. So, next is the case with ionic solids. We have seen that the constituent particles are ions, in which the cations and anions are bound by strong electrostatic force of attraction. We have seen an example of an ionic solid, that is NaCl. You can see here the melting point of NaCl is 801 degrees Celsius and boiling point is even higher, it is about 1465 degrees Celsius. Ionic force operating between them is very strong, or the constituent particles are held together by very strong electrostatic force of attraction. So, that much energy is needed to break these bonds, and that is why ionic solids are characterized by high melting and boiling points. Another case is titanium dioxide, which is again an ionic solid. In titanium dioxide, the titanium oxygen bond, that is TiO bond, is ionic, predominantly ionic, but it also possesses a significant amount of covalent character. And as a result, they have extremely high melting point and boiling point. TiO2 is characterized by a very high melting point of 1843 degrees Celsius and a boiling point of 2972 degrees Celsius. So, among different solids, ionic solids generally have very high melting and boiling points due to the strong electrostatic force of attraction. So, till now we have discussed about the effect of intermolecular forces on the melting and boiling points of various crystalline solids. Now, next we will move on to crystallization. Crystallization is one of nature's most fascinating processes where disorder transforms into perfect geometric structures. On the screen you can see beautiful images of various crystals. You have quartz crystal, sodium chloride crystal, then ice crystals or snowflakes. So, what is crystallization? It is a process in which a crystalline solid precipitates out from its solution state. Okay, from the solution, the constituent particles will be regularly arranged in a well ordered pattern to form beautiful crystals, and this process is called crystallization. Crystallization process is a very common process that we adopt in our laboratories. One of the common methods for employing crystallization is heating a solution containing solute followed by gradual cooling, and upon cooling crystals will start to precipitate out. Now, what happens during this crystallization process? The structural units, that is the atoms, ions or molecules, will arrange themselves into a well defined and rigid arrangement to minimize the energy of the state. A perfect or well ordered arrangement will reduce the energy of the system, which in turn causes a decrease in the free energy of the state. So, minimizing the energy of the state means that there will be a decrease in the free energy of the state. So, during crystallization, the structural units will arrange themselves into well defined and a rigid arrangement to minimize the energy of the state. Now, let us move on to the mechanism of crystallization. Our story begins with a supersaturated solution. Now, what is a supersaturated solution? A supersaturated solution contains more dissolved solute than a saturated solution, and it is generally employed by adding more and more of solute to a solution, and it is dissolved by heating, and we can add more and more of solute until it becomes supersaturated. Now, what happens when a solution becomes supersaturated? The solution will be unstable and it get ready for crystallizing out. As you can see here, the constituent particles will be randomly oriented by receiving excess energy, and these particles will be primed for crystallization to begin. So, in order for crystallization to occur, we need a supersaturated solution that will be unstable and can readily crystallize when disturbed. It will have excess energy, and that energy will be utilized for crystallization to begin. Now, there are two stages of the crystallization process. We will discuss one by one. The first stage is nucleation or the birth of crystals. What is nucleation? It is the formation of tiny ordered arrangements of molecules called nuclei. So, nucleation is the first stage of crystallization or the beginning of crystallization, in which there will be tiny ordered arrangement of molecules, and these tiny ordered arrangement of molecules are called nuclei. Now, this nucleation can occur in two ways. One is homogeneous nucleation. Homogeneous nucleation occurs spontaneously within the solution when molecules randomly collide and temporarily align. Okay. So, the molecules will be randomly oriented they collide with each other and then starting aggregating. So, most of these alignments quickly break apart, but occasionally reaches a critical size and becomes stable. So, such a cluster is called a critical nucleus. So, in this center, this is a nucleus, and when this nucleus reaches a critical size, that becomes stable, and that is called a critical nucleus. Now, next type of nucleation is heterogeneous nucleation. It occurs when molecules align on an existing surface like a dust particle or a container wall or an intentionally added seed crystal. Okay. So, we will have a foreign particle like a dust particle or a container wall, and the tiny ordered molecules can align on its surface. So, that is called a heterogeneous nucleation, and this requires less energy and is more common in real world crystallization. So, we have seen the first stage of crystallization, which is called nucleation, and it is a tiny ordered arrangement of molecules to form a nuclei. There are two ways, it is homogeneous nucleation and heterogeneous nucleation. Now, we will move on to the second stage of the crystallization process, and that is nothing but crystal growth. Once a stable nuclei is formed, then crystal growth begins. So, molecules from the solution attach to the growing crystal faces in specific orientations strongly dictated by intermolecular forces. As you can see in this figure, the first stage is nucleation. There will be tiny ordered arrangement of the molecules. Now, these will come together or agglomerate together to form small clusters, and when these clusters reaches a critical size, then the crystallization will begin, and that will finally lead to crystal growth. So, this is the second stage, that is the crystal growth. Different crystal faces grow at different rates, creating the characteristic shapes of various crystal structures. And the crystal growth depends on several kinetic and thermodynamic factors. And during this crystal growth, the total surface energy of the system is minimized. Here you can see an animated video on the crystallization process. We know that crystallization begins with nucleation, and then small clusters of molecules will begin to form, followed by crystal growth. Further precipitation involves additional nucleation and crystal growth. If the rate of nucleation is greater than that of crystal growth, then we will have a large number of small particles. On the other hand, if the rate of crystal growth is greater than that of nucleation, then a small number of large particles is formed. So, we have discussed two stages of crystallization process. Stage 1 is nucleation and stage 2 is crystal growth, and various thermodynamic and kinetic factors affect the crystal growth. Now, let us see some factors affecting crystallization. Temperature is one of the factors that affects the crystallization process. It affects the solubility and molecular movement. Generally, lower temperatures reduce solubility, promoting crystallization. Crystals precipitate out at generally lower temperatures. Agitation is another factor. It can break up forming nuclei, but also helps distribute molecules evenly. pH also affects the crystallization process. pH or other solution conditions like the ionic strength affect molecular interactions, which in turn affect the crystallization process. Impurities can also inhibit growth or they can create defects in crystals, thereby interrupting the crystal lattice. So, temperature, agitation, pH, impurities and several other factors influence the crystallization process. Now, let us see some real world examples of crystallization. On the screen you can see a beautiful animated picture of the formation of snowflakes, and snowflakes form when water vapor crystallizes around dust particles in clouds. On the screen you can see the crystallization of salt, the crystallization of sodium acetate. It is another example for crystallization. And this is a beautiful time lapse video of the crystallization of metallic copper. So, today in this session we had a detailed discussion on the nature and strength of intermolecular forces affecting the melting and boiling points of various crystalline solids. Then we had a discussion on crystallization and crystallization process. We have seen that crystallization process proceeds via two stages, nucleation and crystal growth. Now, we will have some questions based on today's session. The first question is, what is meant by crystallization? So, we have four options. Option A, concentration of atoms into highly structured form, solidification of atoms into a highly structured form, solidification of solution, concentration of solution. Question number 2, why is a supersaturated solution unstable? Option A, concentration is higher than equilibrium concentration. Option B, concentration is lower than equilibrium concentration. Option C, concentration is equal to equilibrium concentration, and option D contains impurities. Question number 3, the nature of the crystallization process is governed by thermodynamics, kinetic factors, thermodynamic and kinetic factors, none of the mentioned. Question number 4, what is nucleation in crystallization? You have four options. It is the initial step in crystallization, it is the final step in crystallization, it is a step where nucleus is added, it is a subcategory of crystallization. And the last question, what is homogeneous nucleation? Spontaneously generated nuclei, option B, randomly generated nuclei, option C, orderly generated nuclei, and option D, randomly and spontaneously generated nuclei. We will discuss the answers in the next class. Also, we will see more interesting aspects of crystallography in the next class. Thank you.